Okay, welcome. This is week 13 of our semester, the penultimate class. Next week, we'll kind of continue the exploration of higher and higher scales, going from galaxies, which was last week, to the cosmological scale, the entire universe, and its structure and dynamics next week. But today, we're going to discuss an important topic kind of in between the local scale, the galactic scale, and the extragalactic and cosmological scale, relevant to how we find and measure these different scales. And those are explosions and astrophysical transients. So for much of the course, we discussed stars, mainly stars, which are defined by their equilibrium and by the fact that they spend a very long time in the same state, in equilibrium between gravity and pressure and energy production and heat and all of those various equations that we saw for stellar structure. We also saw that sometimes those stars die. They age, they run out of fuel, they die. We talked about the more common low mass stars and how they die, finally ending up in a white dwarf. And we also mentioned neutron stars, which are the end result, neutron stars and black holes, the end result of higher mass stars, which die out in more dramatic effects like supernovae. And we talked a little about some of those effects, but today we'll devote the entire class to things like supernovae, including supernovae, their various types, high energy, and how we can actually see them from very, very far away, most of the time outside of our own galaxy. And in fact, seeing them in a different galaxy can actually help us measure or estimate the distance to that galaxy. And that's part of the distance ladder, which we've been building from the first class in the semester, calculating the radius of the Earth, the distance to the moon and to the sun, and using that to calibrate parallax and higher levels in the ladder. Variable stars, estimating the distance to Andromeda, which probably was a separate galaxy. We did that last week. Supernovae, GRBs, black hole mergers, gravitational waves, all of these tools, which we'll discuss today, enable us to go further and estimate very, very far distances away from the Earth on extragalactic scales and building up to the cosmological scale. So a short reminder, the main sequence of stars, these are the stars on an HR diagram. As you recall, there's the temperature or color, which is the same on the horizontal axis, the luminosity, which can be interpreted either as magnitude or power on the vertical scale. And as stars get heavier and heavier on the main sequence, they kind of climb from the bottom right towards the upper left. And as we saw in week 6 in the tutorial, there's an end or an edge of this main sequence. You don't expect a main sequence star at any arbitrary mass, 2,000 solar masses, 1,000,000 solar masses. The edge is actually a lot lower than that. And we calculated this end, this high end of the main sequence, but considering that a star is in equilibrium between gravity and pressure, when the star is more and more massive, it gets hotter and hotter because radiation pressure grows like T to the 4th power, while gas pressure is only linear in the temperature. In high masses and high temperatures, it's radiation that dominates, the radiation pressure. And then if you compare the radiation pressure to the gravitational pull of the mass of the star, you find that they equal each other, and basically you can no longer have stability above a certain mass. The pressure will grow stronger than the gravity, and the star will start to disperse. It won't be held in together. It will not be a bound system. So under those assumptions of hydrostatic equilibrium, radiation pressure balance and gravity, and spherical symmetry for the geometry of the star, we found what's called the Eddington Luminosity, which is about 40,000 times the solar luminosity, or which is given by about 40,000 times the solar luminosity times the mass in units of a solar mass. And if you calculate the exact position where it ends, then that happens around 70 solar masses with an Eddington luminosity of about 3 million solar luminosities, which is about 10 to the 33 watts, or in astronomical units, 10 to the 40 erg per second. That's in CGS. And that explains why we actually see this main sequence kind of dwindling and ending around just over 60 solar masses. It's because stars heavier than that can't be bound anymore. The energy that they produce, the heat that they produce from being so heavy, creates so much radiation to come out, and so that it basically disrupts, the pressure disrupts the star itself, and it overcomes gravity. That means that the maximal luminosity we expect from a star is about 3 million solar luminosities, or about 10 to the 33 ergs. That's called the Eddington limit. We do not expect a star to produce more than this. And if we see a star produce more than this, or if we see, sorry, not a star, if we see anything, any object produce more luminosity, more power than this 3 million solar luminosities, one of our assumptions has to break. And typically it will either be the equilibrium, meaning it can't be sustained for a long time, and it will be a transient, or an explosion or something that happens and then goes away. It can't last for a long time. Or you'll have to break spherical symmetry. The geometry of the system will have to change to allow for these equations to hold when you break the bound, break the limit. Or of course, you can break both of these. So this Eddington luminosity is kind of an important factor in astrophysics. It demarcates the boundary between stars in equilibrium, producing energy in a conservative fashion, stable fashion, and things that have to be transient, exceptional, geometrically different, all what will basically be called or described as high energy astrophysics. To put this on a more numerical footing, we'll add one more kind of number into this play, and that's called the Planck-Dyson luminosity. So the Planck-Dyson luminosity asks, what if we kind of ignore the energy production mechanism? So we're not just limited to a star producing radiation pressure in a bound hydrostatically equilibrium system. What if we just allow a completely generic explosion? Just take as much energy as you can and throw it out as fast as you can. What's the maximal luminosity or power that you can get out of any part of space? And we can run this calculation in the following way. The easiest thing is to imagine spherical symmetry, and imagine you have some energy and mass or energy contained within some sphere of radius r. Okay, so if you have a mass m, the energy is mc squared. That's special relativity, and you know that from your first year of undergrad. Now, general relativity tells us that you cannot condense this mass to an infinitesimally small radius, because once you go below the Schwarzschild radius, it will go into a black hole and nothing will come out. So the most you can condense it is basically the Schwarzschild radius, which is 2gm over c squared. Or if you really want to kind of push the edge, you can say it's a Kerr black hole, so it's a spinning black hole, and if it's extremely spinning with the maximal possible angular momentum, then the radius can be as small as Schwarzschild radius will be corrected to about half the regular Schwarzschild radius, just 1 gm over c squared. So this is basically the densest you can push, or the smallest you can push a mass m into a sphere of radius, which is gm over c squared plus epsilon, so just slightly over gm over c squared. Okay, so that's the energy, and that's where the energy is located. Now we want to push the energy out, so to actually radiate it away as power, as luminosity. And so we'll have to ask how long it would take to release this energy from this ball of mass. And the order of magnitude here would be just R over C, because the fastest you can send energy out is at the speed of light, c. And you have to cross a distance of order r, which is the radius of our ball. And so if the radius has to be greater than gm over c squared, then the time for releasing it has to be greater than gm over c cubed. So that gives us a time length which we have to obey. We have to at least use that time to send it out. What then is the luminosity? Power is just energy over time, the amount of energy you can release over the time it takes you to release it. The energy we said was mc squared. We divide it by gm over c cubed. And interestingly, we find that the mass cancels out. We had one mass in the numerator and one mass in the denominator, so the mass doesn't actually matter. And what we are left with are only two bare physical constants, classical ones as well, c to the fifth over g. So c to the fifth over g is already in units of power, energy per time. We recall that in relativistic notation, we call both of them 1. So the Planck luminosity, this limit on how much energy you can release from any area or any volume, any process, this number is just 1 in dimensionless GR units. In general relativity, Planck luminosity is 1, or Dyson luminosity is 1. If you want to calculate how much it is in erg or in watts or in solar luminosities, just plug in C and G in their MKS equivalents, in MKS units. And so we find it here at the bottom of the table at about 3.6 10 to the 52 watts, which is equivalent to about 10 to the 26 solar luminosities. So that's a big number. The luminosity, the physical bound on luminosity is quite large. It's 10 to the 26 times the luminosity of the sun. And recall that the Eddington limit here in kind of light magenta in the middle of the table was only about 3 million, so 3 times 10 to the 6. So we have many, many orders of magnitude, about 19 orders of magnitude between the stable stellar Eddington limit all the way up to the Planck limit. And we can kind of compare these to various processes and ask where different types of energetic processes are located and how to understand them. So obviously the sun here is one of the scales, 1 solar luminosity, 3 million times less luminous than the Eddington limit, but of course, still much more luminous than anything on Earth. So humanity's entire consumption of energy is about 5 10 to the minus 14 solar luminosities, which if you recall from our talk about extraterrestrial life and civilizations, we are very, very far away from the type of civilization which can actually use the equivalent energy production of its parent star. We're not even meeting, although we're very close, to the radioactive production of energy from the Earth with Earth elements like uranium and potassium, which are naturally degrading radioactively at about 8 10 to the minus 14 solar luminosities. We're not even at the amount, what we call the class A type 1 civilization. We don't even use all of the energy our sun sends us at the Earth, which is about 4 10 to the minus 10 solar luminosities, still 4 orders of magnitude above where we currently are. You can see that there was, for a brief instant, a moment when humanity competed on the scale with the solar luminosity. That was at the moment of exploding the largest nuclear man-made bomb ever on the Earth, the hydrogen mega bomb, the Tsar Bomba. And even that was only 1% of a solar luminosity. You might also recall from maybe the first or second week that our sun is actually a very mild star. There are much heavier and more luminous stars, various giants. So Sirius A is just a largish star. It's not even a giant, 25 times the solar luminosity, going up to actual giants like Bellatrix, Rigel, and Betelgeuse, various giant stars in the constellation of Orion. And they can go up to about even 100,000 times the luminosity of our sun, again in a completely stable nuclear burning phase. P Cygni in the constellation of Cygnus is a very, very massive star. It goes to 600,000 times the solar luminosity, still a bit off the Eddington limit, but we're kind of seeing a scale of what these various processes are producing. Noteworthy among these, a nova. We already mentioned this previously in the course when we talked about binaries and a cataclysmic binary, when a white dwarf is being overflown with a companion, igniting nuclear reactions on its envelope. And that's actually quite bright. It looks like a new star in the sky, and it can be as bright as about 10,000 solar luminosities. So it's a very bright transient. Most of these other things are stationary. Going above the Eddington limit, we get to the really interesting stuff. So Eta Carinae is a weird star in that constellation, in that its shape is not symmetrical, and so it exceeds the Eddington limit. It actually emits on a day-to-day basis, as far as we can see, more energy, more power than the Eddington limit accounts for. So that's a very interesting stellar or semi-stellar system to study. Jumping a few orders of magnitude above that, we get to the actual explosive phenomena. An average supernova at 3 billion times the solar luminosity, about 1,000 times brighter than the Eddington limit, comparable, as you see, to the entire stable output of a whole galaxy. So the Milky Way itself is only has about a few 100 billion stars, and so its output is about the average stellar output times 100 billion, which is about what we get here. And a supernova is already at a considerable percentage, something like 30% of the entire Milky Way's output. So a supernova is indeed a super bright event. You can actually see it against the background galaxy. It's as bright as a galaxy in some sense. We mentioned quasars in the last week, those active galactic nuclei, which can in fact outshine a full galaxy. So you would have more energy coming out, more power coming out of the center where the black hole is accreting than the entire stellar output of the whole galaxy. And again, that is because the energy production in accreting into a black hole is much more efficient than just burning nuclear fuel. You're converting the whole, in some sense, the entire mass of the object into energy, not just the nuclear differences between various isotopes and nuclei combinations. If you gather all the galaxies in some supercluster together, like our local one, you get another 3 orders of magnitude higher. But we then do have objects which are as bright as an entire supercluster of galaxies. And these will be just your average gamma ray burst, which we'll talk about more today. Bursts of gamma ray radiation coming from the sky, and we see a lot of those. Even higher up, about 7 orders of magnitude higher, is the peak luminosity of a gravitational wave. Now, this is not of course, in the electromagnetic spectrum. This is the gravitational wave emission. But again, because this is a pure GR process where mass is converted directly into energy, the efficiency is very, very high, and we can get almost as high as 10 to the 23 solar luminosities. It's as bright for an instant. It's as bright as a 100 million 100,000 billion suns. So it's very, very energetic. Still coming only to about 0.1% to the Planck and Dyson luminosity. So we still have this kind of range to go up. So today's class, as I said, we'll talk about kind of the bottom half of this table, the transients and those explosions which release huge amounts of energy, at least for a short time. Any questions?
Can you repeat, please, the last one? What is the peak luminosity?
So as we saw, a gravitational wave is coming from a system, where a system emitting gravitational waves evolves. It has that standard chirp profile, where the frequency grows in time, the amplitude grows in time. And of course, that means that the power grows in time, because power comes from the amplitude and the frequency, some product and square of the frequency and amplitude. So as the process, as it grows, it reaches at some point a maximum, which is more or less where the two black holes either collide or fall on each other, merge, when you basically end the process in a merger. At that instant, or close to that, is the instant of peak luminosity, which is the most energy released per unit time, the greatest power coming out in gravitational waves. And we'll calculate later today how bright that is, and it's quite bright. It comes to fractions of a percent of the Planck-Dyson luminosity. Okay, so we'll start slow or with weak processes, relative, with a classical nova. And we already mentioned these a while ago, so let's just remind ourselves. A nova, the name comes from it being a new star in the sky, comes from a cataclysmic binary system where we have a white dwarf and a larger companion. The white dwarf is more compact, about could be 1,000 or 100,000 times more compact than its partner, which means it can tidally disrupt the partner. Another way to think of it, the large bulky partner can overflow its rush lobe. If you remember, there are the Lagrange points of stability in a two-body system. There's the rush lobe, which is the area or the volume around the more massive large object, or the fatter object is more correct, where mass is bound gravitationally to itself. Overflowing that, it gets disrupted. It's actually more drawn to the companion, and then mass can flow from the bulky partner to the lean, dense partner, in this case, a white dwarf. This matter creates a disk, an accretion disk around the white dwarf. And as the mass kind of spirals in, it gets fricted, it gets friction. The inner parts of the disk are rotating more rapidly than the outer part of the disk. That's basically because of Kepler's law. The closer you are to an object, the faster you rotate. But because the outer part is also dragging the inner part gravitationally, there's a friction effect. So the inner part is dragging the outer part forward. The outer part is dragging the inner part backwards. This kind of what's called dynamical friction moves energy and angular momentum from the inside towards the outside, and it heats the disk. Very similar to the process we talked about last week for AGNs, active galactic nuclei, only there it was a black hole in the center that was kind of fueling the whole system with its gravity. Here it's a white dwarf fueling the system with its gravity, heating the disk and heating the envelope of the white dwarf where the matter is accumulating onto it. If this envelope, which can be mostly hydrogen, because it comes from the bulky partner, which presumably is either made of hydrogen or maybe helium if it's in some giant phase. but mostly light elements like hydrogen and helium. So they're quite easy to ignite at relatively low temperature relative to what we'll see later today for supernovae. And so if it gets hot enough, the disk itself and the envelope will ignite, and we'll have a runaway nuclear process on the outside. In some sense, this white dwarf, which has stopped burning nuclear fuel of its own, is now reignited. It's born again, and it's a new star, or appears as a new star in the sky as a nova. Typical luminosities, as we said, can be about 10,000 solar luminosities. They don't last for a very long time. This is not stable. Note, of course, we're breaking hydrostatic equilibrium, we're breaking spherical symmetry, so, and it's also a non-stable process. It only happens for a short time, but that short time can last for months, a few months or a few years, during which there is a bright new source in the sky. So the first type of transient that was documented, or maybe understood, this nova process. Once the fuel runs out in this runaway process, the system goes quiet again, although it could theoretically reaccumulate matter and then reignite after periods ranging from decades to hundreds or thousands of years, or even hundreds of thousands of years. And we do have these cases of recurring novae. Because binary systems are very, very common in the universe, as we've said, maybe half of the stars are actually binary stars. And because white dwarfs are the most common end state for a star coming out of the main sequence, these scenarios of novae are very, very common. We expect about a few tens per year at every galaxy, even though we can't see all of them necessarily with our own eyes. For example, in our own Milky Way, as we talked last week, whatever happens deep in the galactic disk away from us, we cannot see because dust is basically blocking the way. But we do still see a lot of these, even in our own galaxy and in our near vicinity. It's not very, very bright, so it's hard to see these in faraway galaxies, but at least in our satellites and our near vicinity, we can see many of these. A small nuance here is that this only works if the white dwarf is of relatively low mass. How low? Below the Chandrasekhar limit, the Chandrasekhar mass. If you recall, the Chandrasekhar mass is the maximal possible mass for a white dwarf. That is the maximal mass where electron degeneracy pressure can sustain gravity or hold against gravity. If the companion feeds the white dwarf above the Chandrasekhar mass, it cannot hold anymore, and it will collapse and explode in a supernova. And that's a particular type of supernova, type 1A supernova. Any questions about regular or classical nova? Okay. Then let's go supernova. I see a question. We need the sum of the masses to be less, not the sum of the masses. The mass of the bulky object doesn't matter too much. That's just the source feeding the white dwarf. The nova comes from the white dwarf partner, from feeding and igniting. Now, eventually, if the white dwarf keeps feeding, you'd have to ask what happens to the bulky partner. Does it run out of mass to give? Does it become smaller and then the process just stops? Or does removing mass cause it to expand, in which case it will keep feeding the white dwarf until it reaches some, maybe the Chandrasekhar mass. And that depends on the composition of the bulky one, whether it's in a giant phase or just a main sequence star, the metallicity, the evolution of that object. It is possible that this process would eventually stop, or that it will continue until the white dwarf passes the Chantal-Segal mass. Or of course, as you say, if the sum of both of them is less than Chantal-Segal mass, then it will never go supernova. But even if the sum exceeds, it might not go supernova if the bulky object just stays within its rush lobe. Okay? Okay? Excellent. So supernovae. So the first thing to note here is that supernovae are very, very bright and so very, very noticeable. And people have been keeping a list of them and keeping an eye on them for thousands of years. For a very long time, we have documentations of them from historical records in China from, I think, as far back as the Zhou or Han dynasties. And so even before the Common Era, before the year 0 in the modern Gregorian counting. More recently, and in the West, we've had multiple supernovae documented in the sky. A supernova is designated by the letters SN for supernova, with the year in which it happened. And if there's more than one per year, then we add a letter A, B, C, etc. And we can see that there have been documented events in history of these kind of new stars appearing. Maybe the most famous one, the 1054 supernova, the Chinese supernova or the Arab supernova in the Crab constellation. Today we know the location because it's the center of the Crab Nebula and the Crab pulsar remaining there. Two other famous supernova we mentioned in this course were the Tycho's supernova of Tycho Brahe recognized in 1572, kind of shattering the Western Christian view of the sky as being permanent, the new star. And shortly after that, within 30 years, the Kepler supernova, which his pupil Johannes Kepler saw. And interestingly, after all of these historical supernovae, we haven't seen a supernova in our own Milky Way since Kepler's supernova in 1604. So it's been a long time coming. You can see a few other interesting parameters. For example, the luminosity. This is observed magnitude. So if you recall, we can see to about magnitude 5 or 6, which means some of these are very, very bright. Negative magnitude means very, very bright. These will be brighter than most planets in our solar system. The Chinese supernova is brighter even than Venus. So brighter than the brightest planet in our skies, basically second only to the moon and to the sun. Could be seen in broad daylight, as well as the 185 supernova and the 10,006 supernovae. These are broad daylight supernovae. So they're so bright, you can see them even when the sun is up. The luminosities can go to as high as 1 billion or 10 billion solar luminosities, so a very, very exceptional source. And that's just the brightest peak luminosity. As we'll see, these supernovae, after they appear as a bright light in the sky, they dwindle away over a very, very long time, months to a year. And you can see here how long these stars were tracked for, with the Chinese one lasting for almost 2 years. Most of these were type 1As, although some of them we now think were either 1B or type 2. We'll talk about those different types. And we infer the type of the supernovae mostly from the remnants, from studying what they left behind. So we generally expect type 2 supernovae or core collapse supernova to leave some pulsar behind them, like the Crab pulsar in the Crab Nebula. And we expect 1As not to leave a significant remnant. And so there's kind of an analysis of the remnants, which tells us what these historical supernovae were. Okay. So These supernovae, like we said, can happen very often. They can happen in the same galaxy multiple times. We saw in our own Milky Way, the Tycho and Kepler supernovae only about 30 years apart. And here we have another example, M51 from the Messier catalog, the Whirlpool Galaxy. This is a regular picture from Hubble Space Telescope of that galaxy in 2005 in January. And you can compare that with an image of the same galaxy about half a year later in July, and you see this new light appearing, which did not appear on the left side. Okay, so you can do differential optometry. You put one picture on top of the other and look for differences, and you can either play this with your 5-year-old or with your computer differentiation software and find this light here that's a new star. And you can see that it's actually quite bright, brighter than any specific star in the galaxy, competing in brightness, maybe even with the center. So this is a very, very bright supernova, designated supernova 2005 CS. A follow-up of this supernova in this galaxy year after year amazingly showed a new supernova in the same galaxy only 6 years later. So this light here on the right, you can see does not appear in any of the left images. And so we actually see these transients. We recognize new lights appearing in the sky. You can also see that the 2005 supernova is basically gone by 2011, but a new supernova has emerged. Recall that galaxies are tens of thousands of light years in dimension. So the distance between this first supernova around here and the second supernova here is tens of thousands of light years. And we only saw these about 6 years apart. So it's basically impossible for one of these supernovae to have triggered the other. We can think of them as kind of random independent processes, which give us an estimate of the rate, maybe, of supernova in these galaxies. Another thing worth noticing is that while the galaxy is quite large, both supernovae independently occur in these blue spiral arms. Can anyone think of a reason for that?
Maybe because they are newer?
Which means?
We know that all the giants are basically blue.
It has to do with giants, indeed. It also has to do with what we talked about last week in analyzing these galaxies and the spiral structure. And we talked about the spiral arms being blue and the in-between parts being red and dead. Basically, the older stars that have died and finished their lives are in these red regions, and the blue spiral arms keep forming new stars. And when these new stars are large ones, then they will in fact live for a very short time and then die. And if they're big enough, then they'll die as supernovae. So we trace these type of high energy phenomena, these high energy explosions like supernovae, to the bluer parts of the galaxies, to the spiral arms following star formation. So star formation is, of course, a necessity for stellar evolution, death, and explosions. Okay, and both of these supernovae are type 2 supernovae in the same galaxy, and as you can see, their peak luminosities definitely shows them even against the background. Very, very super bright transients. So what are all these type 1, type 2, etc., these types of supernovae? In this point, we have to remind that astrophysics is an experimental and rather observational science. So we learn things by observation, and we classify things based on observational properties, just like we did for the stellar types in the Harvard classification on top of the age-out diagram. We classify spectral lines and color and brightness and parameters that we can see. We cannot see internal mechanisms or structures. We can only infer them. And so the classification is typically related to what is actually observable. In the case of supernovae, the classification is primarily done based on spectral lines. And the most important spectral lines, of course, are the hydrogen lines. If you don't see hydrogen lines in a supernova, that immediately indicates type 1. If you do see hydrogen lines, that's classified as type 2. So the first thing you ask is, are there hydrogen lines? If it's type 2, so you have hydrogen, you have the lightest element. You then look for heavy elements, some of the heavier ones created in regular stellar life, and that's silicon. Because once you get to silicon, you're basically almost done with the life of the star. So if you see silicon lines, no hydrogen, but you do see silicon lines, that's classified as a type 1a supernova. And the process for these is what we talked about, accretion onto a white dwarf. So the white dwarf, of course, has no hydrogen because it finished its life and moved into a white dwarf phase, either helium or carbon oxygen or something like that. So hydrogen is missing, but heavier elements are still there. So that's a 1A supernova. Any other type of supernova, we still distinguish between type 1C and 1B. 1 means that there are no hydrogen lines, but 1B and 1C means that it does have silicon lines. So it doesn't have silicon lines, so it also doesn't have the heaviest regularly produced elements. But then the distinction is between yes or no helium lines. If it has helium lines, it will be type 1B, and if it doesn't, then type 1C. So that's an observational classification. Physically, structure-wise, both type 1, or the three types, 1B, 1C, and type 2, so everything here that's not a type 1A supernova, is not accretion on a white dwarf. It's a core collapse supernova. It's a massive star ending its life and collapsing, having its core collapse when the fuel runs out, and then explode as a supernova. Okay, so that's the distinction between core collapse or white dwarf accretion. So 1A supernovae and basically everything else. Type 2, type 1B, type 1C. And we also have a minor distinction between type 2L, which is linear, or type 2P for plateau, which is whether we see the light decaying directly in the light curve or whether there's some plateau and only then a decay. Okay, let's take a break until 1 o'clock and then continue with typical parameters for these various types of supernovae. Any questions?
Can you explain the direct decay? What does it mean?
So you can see here the difference between type 2L and type 2P. This is days after maximum and the brightness or magnitude in astronomical terms. You see that these supernovae typically rise very, very bright, very, very fast and very, very bright in magnitude. Here it reaches, for example, 0, normalized to the maximum. So it peaks at 0. And then here you have a direct decay, which is just a sharp line. And then it plateaus into a different slope, or it changes into a different slope, but you have basically 2 straight lines. That would be type 2L supernova for linear decay. You can see in this type 1 supernova as well, type 1A, it would go up and then basically down in two lines, down fast and then down slow. Type 2P is more complicated. You see here that the first line kind of plateaus or evens out, rolls off, and then starts decaying again, and you get these bumps in the decay profile. That would be called a type 2P with a plateau. Okay?
Okay.
Any more questions? Okay, I'm pausing the recording. Okay, so here again we see characteristic parameters for various supernovae, type 1a, 1b, and type 2. And we can see those typical luminosities, around 10 billion solar luminosities at the source, so very, very bright objects. The ejection velocity, the very fast velocity at which mass is being thrown out of the supernova from this explosion, with masses of 1 to several solar masses in the ejecta in this tremendous speed. 10 to the 4 kilometers is approaching the speed of light, or a significant fraction of the speed of light, 3 times 10 to the 5 kilometers per second. So it's about 3% the speed of light. Like we said, type 1a star is always a white dwarf. It's the accretion of matter on a white dwarf, causing it to pass the channel of Sekar mass. And type 2 being typically from supergiants, very, very massive stars, aging, running out of fuel, and then exploding. And we see these profiles, typical profiles of what they look like. Luminosity in all of them grows very, very fast, and then decays in these 2 clear, distinct slopes, a fast decay and then a slower decay. The fast phase lasting an order of 50 to 100 days, and then switching into a slow decay phase, which can last for even order of a year. Okay, so a little more about these type 1a supernovae. We have here on the right an image of one of these from 1994. This is not in our galaxy. It's outside the galaxy in the new general catalog, numbered for galaxy number 4562. This is again a Hubble Space Telescope image, like most of other pictures that we see of these beautiful supernovae. We see it's very bright, again, comparable with the galaxy itself. We see the same light curve from the previous slide, rising very fast, decaying very fast, and then switching to a lower slope. And as we said, type 1a supernova are always the result of a white dwarf eating too much, feeding past its limit, the Chandrasekhar mass at about 1.4 solar masses. When that happens, it overflows it exceeds the Chandrasekhar mass, the pressure can no longer hold it together, and it explodes completely, leaving typically no central remnant behind, no pulsar or something behind. The entire white dwarf is disrupted and explodes. An interesting thing about these supernovae is that because the process is always a white dwarf exceeding the Chandrasekhar mass, they always happen at the same mass, which is the Chandrasekhar mass, which means all the type 1a supernova that we see are basically the same one, the same explosion happening over and over again in the exact same conditions. Up to very, very small variability in the composition of the white dwarf, metallicity, etc. They're basically the same explosion, which means it's become a standard. It's a standard explosion, or what we call in astrophysics a standard candle. It's kind of a beacon in space, which is always the same and always shines with the same brightness. And as we saw already for Cepheid variable stars and for other types of objects, if you know exactly how bright something should be at the source, and you can measure how bright it appears to you, the difference between those two tells you exactly how far away it is. So these standard candles are actually our standard rulers for measuring large distances inside and outside the galaxy and between us and galaxies where we see these supernovae. So generally, if we see just a galaxy in the sky, like we saw last week from the Tully-Fisher relation, we can estimate how far it is based on the expected brightness, by the mass, by the velocity. We have to use a lot of parameters to infer the distance. But if we see a type 1a supernova in that galaxy, that is a supernova which has no hydrogen lines, but does have silicon lines, we know the mechanism, we know the mass, we know exactly what the absolute magnitude should be. Comparing that to the observed magnitude, we can find a very good estimate for the distance to that galaxy. In fact, the Tully-Fisher relation is normalized or calibrated by using galaxies for which we can estimate the distance well by these standard candles in those galaxies. Okay, we expect them to be quite common, about 3 per century on average in a galaxy like the Milky Way. It's actually considered exceptional that we haven't seen one in our own galaxy for about 400 years. So any day now, we expect a supernova in our galaxy, although this any day can, of course, take 30 to 100 years or 400 years, and statistics are always a fun thing to play with. Now, regarding those slopes of the decay, today we can analyze the spectrum and analyze what is causing these different decay profiles and the light coming into these two stages. And it's not the first explosion that we're seeing. The stages of the decay come from a different physical mechanism. They come from radioactive decay in two stages, nickel to cobalt, and then cobalt to iron. So these elements are very close to each other around the iron peak. They all have atomic mass number of 56, as you can see, so 56 nucleons. They differ by atomic number, so by the mixture of protons and neutrons among those nucleons. So what happens in the explosion is that we kind of charge, or rather give energy and store energy in these radioisotopes. But then as those radioisotopes decay back to more stable ones, they emit photons from the energy gain during those decays, both photons and neutrinos. So we have photons, gamma photons and neutrinos. And those are the ones that we see. We could see the neutrinos, and we typically see the photons, it's either gamma or even in the optical. So the slope is then understood as a difference between the radioactive half-lives or decay rates of these various isotopes. So the first one, nickel 56, has a half-life of 6.1 days. And on average, or about half of that nickel will decay to cobalt 56, that is, exchange one proton to a neutron by emitting a positron and the corresponding neutrino and a photon. So this decay of a proton to a neutron, electron, and neutrino will happen spontaneously on average after 6.1 days, or half-life of 6.1 days, and that explains the decay rate. This process can happen in another channel. It can also happen by electron capture, which is a very similar process. In this process, the nickel nucleus absorbs or captures an electron. The electron then fuses or merges with the proton, again turning it into a neutron, emitting a neutrino and radiation. The difference is that the first process is completely spontaneous. It's a proton emitting a beta plus particle, emitting a positron spontaneously, turning into a neutron. The second one, a proton absorbs an electron which came from the outside, which was around an ambient electron, again turning into a neutron and emitting a neutrino. The second stage is very similar, but instead of nickel to cobalt, it's one step further, cobalt to iron 56. Again, a proton can spontaneously decay into a neutron by releasing a positron and then a neutrino and some radiation with a half-life of a longer half-life of 77.7 days, or a non-spontaneous process by capturing an electron, but the end result, the net result is the same. They're just different processes in the sense that the first is spontaneous and the second is stimulated with electrons. Because the half-lives are about a factor 10 or 12 apart, you can see that the second stage is much, much shallower. It takes a longer time with a lower slope. The energy release is slower and it takes a longer time because basically the exponential decay rates differ by about a factor of 10 or 12. Any questions?
I have a question, a weird one.
Yeah.
But the supernova we see right now has like some sort of an X luminosity thingy. Is that just an effect by the telescope?
Yeah, that's a telescope thing. Basically, coming from the lens. It's an optical effect of lenses and mirrors and what holds them together. Okay. It's not coming from the actual supernova.
Okay, I thought so. Then no questions. Thank you.
Any more questions? Okay. Supernovae can leave remnants behind. Typically, the 1As will not leave a remnant. Or here we have they will not leave a central object in the remnant. Obviously, throwing away mass, the mass will expand at a very high velocity. And after a long time, you can kind of see this cloud or this bubble expanding from where the star had been. This here is Tycho's supernova remnant. So we know its position and time very accurately because Tycho kept very good notebooks of his measurements in 1572. And this is an X-ray photo of Tycho's remnant. And we can see how this kind of cloud remnant is growing in time. It's been about 450 years since this new supernova exploded. Two type 2 supernovae. The left one here is the Crab Nebula, the remnant of the 1054 guest star supernova. This is an optical image from 1955. And on the right, we have the Cassiopeia A remnant, a supernova, which was not documented as it happened. So we don't know exactly when it was. It's about 330 years ago, but the estimates differ by as much as 40 years, plus or minus, in various records that might have indicated this supernova. And again, we see these kind of typical shapes of these clouds or nebula growing as spheres, as spherical shells, expanding out, very bright in X-ray. There's a shock, a blue shock on the outside as the expanding cloud hits the interstellar medium. In the case of Cassiopeia, there's also, if you notice, an X-ray source right in the middle of this sphere. This little dot is an X-ray source, and that's what we believe to be a pulsar, which is a neutron star remnant of these explosions. Core collapse supernovae do typically leave a remnant in the middle. We know there's a pulsar in the center of the Crab Nebula, the Crab pulsar, probably one of the first ones actually detected in the early 60s. So what are these core collapse supernovae, which are a completely different process from the white dwarf accretion 1A supernova? For that, we have to kind of go back to our class about stellar evolution and the lives of the stars and remind ourselves that the fate of a star depends on its initial mass. All stars start on the main sequence. And here we have the main sequence in a logarithmic scale of masses. But the low mass stars will just turn into red giants, go through maybe a helium flash, continue with some emitting a planetary nebula around them, but basically live out their lives and finish their lives as white dwarfs, either directly or indirectly, but finish their lives mildly as white dwarfs. Heavier stars, starting from about 8 solar masses and above, will go through a much more violent evolution. They'll turn into a supergiant, exhaust their nuclear fuel, and then finish off their lives in a supernova, which, if for intermediate mass stars, will leave behind a neutron star. For higher mass stars above the limit for a neutron star, the TOV limit, will leave behind a black hole. So on the right here, we kind of see the same example with more specific numbers, kind of measuring the mass of the hydrogen, of helium, and then the range for finishing their lives as supernovae after a helium flash, possible carbon flash. Eventually, the most massive stars here above about 8 solar masses. We have completion of the high level of element production after hydrogen, helium, carbon, and then oxygen, silicon. And once we're all the way to silicon, it will basically burn to iron and completely exhaust the nuclear fuel and then explode. So how do we reach from a main sequence star all the way up to a supernova? So if our star, as I said, was massive enough to begin with, above about 8 solar masses, it will take a very long time to cook the conditions until they're ripe, but eventually it will happen. And it will happen in various stages. The first thing is that when the star exhausts its hydrogen content, as we mentioned before, if it's massive enough, its core will be hot enough and above about 100 million Kelvin and a density of about 10 million kilograms per meter cubed, it will ignite the triple alpha process. That is merging heliums to carbon. First, 2 helium nuclei merge for beryllium. If you recall, beryllium is a very, very unstable nucleus. So if the temperature and density are not high enough, this beryllium will spontaneously decay and nothing will happen. But if the density and temperature are hot enough, then during the fraction of time, if I recall correctly, it's something like 10 to the minus 12 seconds before the beryllium spontaneously breaks apart, it can absorb a third helium nucleus. And then that's the 3 helium, this triple alpha process, producing a carbon nucleus. This arrow going back and forth reminds us that this process goes both ways because, as I said, the beryllium is unstable. So even if it forms, it will most of the time break back to helium or heliums. But if it's dense and hot enough, we'll have carbon production. After that, the carbon can continue to absorb more helium nuclei, going from carbon to oxygen, from oxygen to neon, and above about 600 million Kelvin, the carbon can absorb one carbon nucleus can absorb the next carbon nucleus directly, not just grow one helium nucleus at a time, but merge carbon-carbon reactions, and then already get oxygen. And then neon, I don't know what Na is in English, but then magnesium and higher elements. Okay. Above 1 billion Kelvin, the oxygen can itself fuse with another oxygen. And again, we have these higher and heavier elements: magnesium, silicon, potassium, and sulfur. So producing silicon happens at about 1 billion degrees. at 3 billion degrees, so we're kind of running out of all these lower fuels. The core is condensing more and more, heating more and more, getting more and more dense. And then eventually, at 3 billion Kelvin, we can start burning the silicon itself. So the silicon itself can absorb helium and produce these higher elements, sulfur, argon, all the way up to iron and nickel. So the kind of the iron peak. All of these arrows here go both ways, which means that at this high temperature, the process is reversible. Basically, we're hot enough that the energy gain is no longer that significant. The process becomes a two-way process. It can go both ways. The whole system is starting to become unstable. It could go one way, it could go the other. It's hot enough to overcome all the energetic barriers. And we have kind of equilibrium or unstable equilibrium between these various nuclear processes. Also worth mentioning is that all of these reactions are fast reactions. You can see that the right-hand side involves no neutrinos. If there are no neutrinos involved in the nuclear process, that means the weak interaction is not involved. And if there's no weak interaction, then it's only the strong interaction, the strong nuclear interaction, which means it's a fast reaction. So these things happen very, very fast. In fact, the last period of silicon burning is basically just 1 day after the star's life, which could have been hundreds of millions of years. The last day basically is this silicon burning, a strong interaction mediated reaction. What happens when we reach this silicon burning phase and kind of run out of silicon? As you recall, all of these nuclear reactions only happen in a very narrow temperature range, the Gamow peak, determining the energy required for penetrating the Coulombic barriers for these nuclear interactions to take place. The star is, in this case, is still stationary. It's still in equilibrium. It won't last for a very long time, but momentarily it is in equilibrium, which means the star has a layered structure or an onion structure, with temperature being maximal at the center, temperature decreasing outwards, and with the temperature and the pressure, there's a layering of elements, the lightest elements being on top, and heavier elements towards the center. So we go from the outside, from hydrogen and helium, down through carbon, neon, oxygen, magnesium, silicon, all the way down to the core of nickel and iron. And that core is inert. If you recall, from I think week 3, the binding energy per nucleon plot here on the right shows that around iron 56, the binding energy is at a maximum. That is, we can no longer produce any more energy by changing this element into, or isotope, into anything else. So hydrogen on the left likes to fuse, or can preferentially give us energy by fusing higher and higher up into the right until iron. Elements on the right, like uranium, plutonium, can give out energy by going to lighter ones, by breaking apart, by fission to lighter elements towards the left. But with iron, there's nothing you can do. It will not produce any more energy in nuclear processes by itself. So the core becomes inert in this case. And as I said, this core collapse process is the same whether we're talking about type 2, type 1b, or type 1c. The difference is that type 1b and 1c are missing some missing hydrogen lines, which makes them type A. They're missing some of the external layers of this onion structure. And that can happen if, for example, there was a partner which stripped away the higher levels of the atmosphere, or the higher levels of the higher layers of the star. But they're not the ones involved in this core collapse. as opposed to a white dwarf type 1a supernova, where it's the outside that's igniting. In a core collapse, it's the core that's driving the mechanism, so it doesn't really matter what's on the outside. It's only the core that matters. And this core, which you can again see here on the right in kind of in terms of mass, typically if we have a fiducial 25 solar mass star, we see that something like 10% of that will be in the inert core. So just above 1, maybe 2 solar masses are going to turn into iron before this thing stops and breaks down. Okay, so that's kind of the snapshot image of our star and its layered structure just before it goes boom. Any questions so far?
So does that mean that after a star collapses, it has an iron core somewhere, or does that explode as well?
It hasn't collapsed yet. We're preparing the star for the core collapse, right?
Oh.
We burned hydrogen to helium, helium to carbon, carbon to oxygen to neon to silicon, silicon to iron and nickel. And now we have this image of the star. The core is now inert. It's not producing any more nuclear energy, but it's still very, very dense and very, very heavy and very, very hot.
Mm-hmm.
And now it's going to explode.
Oh, okay.
And as we said, the high temperature and density means that the iron in the core can actually break back into lighter elements. It can go photodisintegration. Now, what does that mean? You can't produce energy from the iron, right? It's the most stable in terms of binding energy, the most stable nucleus. You can't gain any energy from it. But if you give it energy, you can use the excess energy to break the iron into smaller elements, which themselves are less stable, but you gave it energy. So this process will not be spontaneous and it will not be exothermic. But if you give it hot enough photons, then you can trigger the iron to break apart. As we said, the temperature is already hundreds of billions of degrees Kelvin, which means the ambient photons, the black body high temperature photons in the core are themselves enough to break apart the iron nucleus. They're even hot enough to break the helium nuclei, which means that the non-spontaneous process of a very energetic gamma photon hitting one of these nuclei can break them apart, can cause it to disintegrate, and that's called photodisintegration. Disintegration triggered by very high energy photons. That means that the iron can break apart, can break back to helium, to 13 nuclei of helium, plus a few excess neutrons. And those helium themselves can break apart to individual protons and neutrons. Okay, that's photodisintegration. But the core is now, again, so hot and so dense that all of the protons and the electrons floating around it are themselves squeezed onto each other. They're pushed together. And when they're pushed together with enough energy, they can merge in an inverse beta decay. In inverse beta decay means that instead of a proton, for example, emitting a positron, creating a neutron in the neutrino, or a neutron emitting an electron in the neutrino, turning into a proton, the proton here can absorb an electron, creating a neutron. So if you look at it as an equation, kind of moving the electron to the right side will be a beta decay, a proton decaying into a neutron and an electron. Or if you move it to the other side, a neutron and a positron, an anti-electron. If you move the electron to the left, it's an inverse beta decay, a proton merging with an electron, forming a neutron and a neutrino. And this is good because we're way above the Chandrasekhar mass. The electrons can't hold the star together. The electrons have nowhere to go in phase space, so they would go into the protons and create more neutrons. The neutrinos take most of the energy, about 99% of the energy of the process is scattered away with neutrinos. Neutrinos have a very low cross-section, so very low opacity to processes, so they basically escape. But the neutrons accumulate in the core. Okay? The electrons are being removed from the core, and neutrons are being accumulated instead of the electrons. What that means is that the pressure of the electrons holding the core is dwindling and is basically collapsing. The pressure is going away because the electrons are merging with protons. They're not supplying the Fermi resistance anymore. But gravity is still there because much of the mass is still there. So if in typical hydrostatic equilibrium, you have a balance between gravity and electron degeneracy pressure, that is gravity pushing inwards, electron pressure holding out. If the pressure is gone, the gravity will collapse the star, collapse the core. And that's what happens in this core collapse. Sorry, that's what happens in this core collapse supernova. Until the collapse, before the collapse, the core was basically behaving like a white dwarf. It had a mass about or just above, just around the Chandrasekhar mass. It has a radius typical of a white dwarf, about 6,000 kilometers, something like the Earth, only mostly iron, nickel, and other iron peak elements. Very, very dense, held together, as we saw, by electron degeneracy pressure. Removing the electron degeneracy pressure, gravity basically has no more opposition. And if there's no opposition, then we already saw the time it takes a cloud of gas to collapse gravitationally without pressure is just a free fall time. And that's basically what it takes, calculated from G, Newton's constant, and from the density rho, which you can just get by the mass and radius. And so you get these typical numbers of about a second or a second and a half. That's the free fall time. So once this process starts, photointegration, disintegration, the iron breaks apart into neutrons, protons, and electrons. The electrons are swallowed by the protons, forming neutrons. And now no pressure can resist this gravity. The core collapses in an order of a second or so. So it's a very fast process. The thing that would stop the collapse, if the star is not too heavy, is the neutron pressure. The neutron degeneracy pressure replacing the electron degeneracy pressure. And so the core of the star will change, will shrink or collapse from a white dwarf size and composition all the way down to a neutron star composition. That is about, instead of 6,000 kilometers, about 10 kilometers of pure neutrons, neutron matter. That collapse releases the gravitational energy in the collapse, about 10 to the 46 joules. As we said, 99% of that goes away in neutrinos almost immediately, and the rest in basically the explosion around, which we see as an optical or gamma ray or all the other wavelengths of the supernova. If the star is too heavy to even create a neutron star, as we said, there's the limit for a neutron star is about 3 solar masses. We don't know exactly where it is. Above this limit, the star will collapse, the core will collapse directly to a black hole. And so the remnant will be a black hole. Okay. So this is kind of a summary of what happens. The core collapses, releasing a lot of energy, most of it in neutrinos, about 1% in kinetic energy, and another 1% of that in photons. And here we have it on the left, on the right as well. The collapsing core here in the center. When the core collapses, everything outside of the core, which is the envelope, falls on top of the core. Because again, if the core collapses, the pressure that the core provided is gone. So nothing is holding the envelope. And so all of the star falls on the core. That's a slower process because it's bigger and less dense. And eventually it hits the new neutron star, which formed very fast. Now, if you ever threw a tennis ball on a wall, you know it comes back to you at the same velocity. If on the other hand, you throw a tennis ball at a car driving towards you, the tennis ball will come back at you faster than the velocity that you threw, because you have to add the velocity of the car. You have more kinetic energy. So when the envelope of the star now collapses onto the core, it bounces back, but it has the excess kinetic energy coming from the core, because the core itself is releasing these neutrinos, photons, and kinetic energy. And so the envelope falling onto the core bounces back with more energy than it had before. And it has enough, and typically it would have enough energy to unbind it, to escape the gravitational well. And so the core of the star collapses, the envelope of the star falls down, bounces back in a shock, and disperses in an explosion. And that's the remnant that we see. The envelope of the star, everything around the center, around the core, being thrown off away to infinity. So that's the spherical bubble, the almost spherical bubble that we saw that expands. That's the supernova remnant. And in the middle, we have the remnant star, the pulsar. So this was all theory, established and developed with theory until 1987, when supernova 1987A exploded very close to us, not in the Milky Way, but in our close neighbor, the Large Magellanic Cloud, LMC, a satellite galaxy to our own, only about 50 kiloparsecs away. And we actually measured neutrinos coming out of this explosion. And they came out within tens of seconds, so very, very fast, the process of the neutrino release. Much, much faster than the photons arrived. The photons only started arriving 3 hours later, because again, the neutrinos are released immediately in the photodisintegration process. The photons coming out still have the whole envelope of the star to plow through on their way out. And as we recall, stellar environments are very, very opaque. It's hard to see photons coming from the center. It's only as the envelope expands enough to become dilute to allow photons to come through that we start seeing photons. Neutrinos have very weak interactions, so they don't interact with the matter. We see them almost directly. The light we then see is the photons. It's the photons which take a long time to get to us, not necessarily the photons created at the explosion itself, because they have the whole star to go through, but the photons created by thermal and radioactive processes through the expansion of the bubble, right? We don't see the photons directly from the explosion. And as we said, that process can take weeks, months, and even years to reach us, or to escape from the bubble and then reach us. Okay, so we mentioned those two subcategories, 2L, supernova 2L and 2P, with the plateau or without the plateau. We associate these today with the environment of the explosion. That is, whether there was if the environment is clean, then the process is basically straight. We see it go up and then go down. If the environment is messy with dust and gas and other matter, then it will kind of absorb some of the photons and cause a plateau, because it will cause a delay in the photons reaching us, and that delay will stretch out the process, creating a plateau. There are other more subtle types, type 2b, type 2n, which are core collapse supernovae that do have narrow hydrogen lines, or that have hydrogen lines which appear and then disappear. But we're not going to focus on these. Just note kind of the standard or typical shapes. A few tens of days, maybe up to 50 days for the first part of decay, and then order of a year for the slower decay of the light curve. Any questions up to now about core collapse supernovae?
So I have a question. The light that we do see is the light from the bubble itself.
The light from?
The luminosity that we see from a supernova is the light from the bubble expanding, and photons trying to burst through that bubble to us?
Yes, it's photons trying to get to us through the bubble, but of course, as they do so, some of them can also thermalize, and we get scattering and heating and re-release of photons, so thermal emission, plus radioactive emission from all these isotopes decaying in the expanding bubble. Mostly, like we said, nickel and cobalt.
I see.
And that explains the slope of the curves as well. The nickel decay and the cobalt decay.
Doesn't the neutrinos collide in each other, causing maybe friction? And
neutrinos?
Yeah.
Neutrinos are only involved in weak interactions, the weak nuclear force, which is very, very weak. And the cross-section is in most cases insignificant. So, supernova 1987A, we saw lots of photons. We saw supernova in the sky. We saw a lot of them. From the entire explosion, we saw 2 neutrinos. And we know that 1% of the energy release is in photons. So 0.1% or even 0.01% of the energy is in photons. 99% of the energy is in neutrinos. Still, we only measured 2 neutrinos and a lot more photons. And that's for the same reason. That's because our detectors are very good at detecting photons and terrible at detecting neutrinos, because neutrinos have a very low cross-section, so they're very hard to detect. You need a huge mass to serve as targets for the neutrinos to interact with. So the neutrinos are basically fly out like a knife through butter. They don't feel the envelope, they don't have interactions, they just come straight to us.
Thank you.
Okay. Let's talk about nucleosynthesis. So we talked about elements being created during the lifetime of a star, right? We started with hydrogen producing helium, helium producing carbon, then neon, oxygen, nitrogen, higher and higher, heavier and heavier elements, up to iron. We can see in the relative abundance of elements in the universe by atomic number that those are in fact the more abundant elements. Hydrogen, of course, most of the matter in the universe, followed by helium. Those were created already in the Big Bang or following the Big Bang. After that, there's a large drop for elements which were only created in trace amounts in the Big Bang and are not necessarily very stable. And after that, we start having all these elements created by successive phases of nuclear burning in stars. And not surprisingly, the heavier elements are harder to produce. So we get this general downtrend. Although there is an accumulation around iron because it's the most stable one. That doesn't explain where all the elements heavier than iron come from. Because again, a star cannot burn iron into a heavier element. There's no energy gain there. And once the star reaches the point of being composed, having a core composed of iron, it will explode in a supernova. But what happens then is that the supernova itself, as we saw, produces lots and lots of neutrons. And when the star explodes, it basically seeds whatever heavy elements are around it with more and more neutrons. So we get neutron-rich material. And these type of processes are represented here. We have an atom with atomic number that is proton number Z, mass number A. If it absorbs a neutron, then the atomic number Z doesn't change, the element doesn't change, but the isotope changes. It can absorb another neutron and emit some radiation. But then these nuclei, if they're unstable, can beta decay. That neutron can turn into a proton while emitting an electron and an antineutrino. And these kind of cascades can happen where the supernova creates higher elements. See, the Z number increases by seeding heavy elements with neutrons, and then they will decay back down or back up to more protons, and then to heavier and heavier elements. So we think that all of the elements heavier than iron basically have to be produced by these types of high energy processes, either these supernovae or, as we'll see, by binary neutron star mergers, where you just mesh together or merge together two big blobs of neutrons, and then obviously you have many, many neutrons to spread around. We distinguish between two processes of neutron capture, the slow or S processes, and the R or rapid processes. S processes means that you're capturing neutrons, but you're doing it one by one. It's a slow process. There's a slow flux. You capture one, maybe you beta decay, capture another one, maybe beta decay. Basically, it means that if you have a chance to beta decay, you'll do that before capturing the next neutron. While R process means that there's a large flux of neutrons and you can absorb many of them at once. This distinction means that, that if we look at what an S process enrichment can do, here we have the neutron number going to the right and the proton number going up. If we start, for example, with silver, then we see that if silver absorbs a new neutron, it reaches a point which is unstable. There's no stable isotope of silver with 110 neutrons. So it will very quickly beta decay into the next element up in proton number, cadmium. One neutron will decay into a proton, we'll get to cadmium. Cadmium does have multiple stable isotopes, so it can absorb 1, 2, 3, 4 neutrons. When it absorbs the fifth neutron, that's very unstable. It will decay to indium. Indium will then absorb a neutron, decay immediately to, I think it's strontium, but I don't remember. And then that can grow all the way up to 121 atomic number, which is unstable, and go into antimony. So we see that there is a chain here, an S process chain, very, very well organized, by which you can produce higher elements. But we also see that there exist isotopes in nature which cannot be reached by the S process. For example, cadmium-116 would have to absorb 2 neutrons at once from a stable isotope to be reached. And that can't happen when you absorb one by one, and after the first, decay in a beta decay. So we have islands forming off, S process islands, distinct, isolated bunches of isotopes which cannot be produced. We have another example here at the bottom. With typical chains, this one has multiple nodes. Cesium can increase in neutrons from 133 to 136. And there are 2 points at which you can go through beta decay, either at 134 or 136 to barium. So this, for example, is a chain which can be completed. But on the right here, we again see that there are these points where the S process chains finish. We can't go above bismuth or polonium. In fact, we can't create polonium in this S process, because what we would have created, polonium to 210, is unstable. It will decay back, emitting an alpha particle to lead. And basically, the whole process here terminates back in lead, a very stable nucleus. Okay, you can go up, you can go beta processes up and to the left. Neutron capture goes to the right, and then finally, alpha decay is going two steps left and downwards. So there are still elements which are inaccessible to S process chains. They need to absorb too many neutrons at once. That requires R processes. And here we have kind of these chains of R process path by which we can enrich our typical stable isotopes. That's this kind of line of stability in the center. We can give it many more neutrons moving to the right and kind of grow the process to rarer and rarer elements and heavier and heavier elements by giving them a lot of neutrons, basically all the way from the stable line of stability all the way to the right. And only when we reach one of these lines, we'll start beta decaying back up. Okay, there are two processes here. There's neutron capture going directly to the right, gaining more neutrons, and then beta decay going to the left and up, converting some of those neutrons into protons until you reach back the line of stability. Okay, so you need the R process to really produce these kind of heavy elements which are disconnected from just S processes from the line of stability. If we look at the periodic table, we can see all of that kind of summarized. Hydrogen, helium, and some lithium are produced in the Big Bang. We have all those yellow elements, which are produced normally in up to iron in stars throughout their lifetime in massive stars, then spread out to the universe in these supernova explosions. Some elements being produced in green with low mass stars as they die, and we still have to explain the purple ones, the ones which are going to require these R process types. Here you see again lead, which is kind of the end of where stars can die, of what dying stars can do, and above that it's straight purple. We're going to require R process to occur, and for that we'll talk after the break about binary neutron star mergers. Any questions? Okay, if not, let's start again at 2:05. Okay, so we talked about supernovae and type 1a, and then type 2 and 1a and 1b and 1c, core collapse supernovae, 1a, 1b and 1c. And those core collapse supernovae, typically what happens is they throw away matter into space, they throw away neutrons, they enrich those elements and make heavier neutron-rich elements and then proton-rich elements by beta decay. But they leave behind the core. That core, which accumulated many, many neutrons from photodisintegration, can be left behind as a remnant. And that remnant is the neutron star and what was discovered originally as pulsars. So what is a pulsar? I think we mentioned this earlier, but we'll just give a reminder. For example, in the Crab Nebula, the remnant of the 1054 Chinese Arab supernova in the Crab constellation has a pulsar in the middle, and that means that we see pulses of radiation coming out of it with a very regular period and shift. The period is 33 milliseconds. So this pulsar actually spins 30 times a second. We now know it comes from a spin. And that spin is not constant. The rate is changing. It's getting longer and longer by a very short amount, 38 nanoseconds a day. Okay, so that's about a million times less than the 33 milliseconds, but every day. So after about maybe a million years, it will be twice as long. So there's the change of the pulsar. The period of the pulsar changes, and Yehu in the tutorial will calculate specifically how we can use this kind of a model for this to calculate the age of the pulsar and the magnetic field of the pulsar from this decay rate. Looking into this Crab Nebula, we can find the pulsar in both the on state, where we see the light, and in the off state, where it disappears. So these pulses are indeed very interesting to look at, a very regular, bright source, which just seems to turn on and off. Here we have invisible light and in X-ray light. So a very prominent source in the sky. Again, in our galaxy, a remnant of a supernova in our own galaxy. And so the discovery of these pulsars in the late 60s was a very interesting thing. They were discovered, as we see here on the right, from the first pulsar discovered by the Cambridge group, Anthony Hewish and his student at the time, Jocelyn Bell. She discovered these repetitive pulses coming one after the other. It's been made into a very famous album cover since, realizing that the shape can differ a little, but basically they repeat after each other at basically the same period. So and it happens both in radio and X-ray, and as we saw for the Crab pulsar, in visible light as well. The periods are very, very short, and they first jokingly suggested to call them LGMs, or little green men, for aliens trying to transmit. Later established as pulsars. This is the CP, the Cambridge pulsar, or what is today just designated as PSR for pulsar, with the sky coordinates in which it was detected. The explanation for these pulsations, as we've mentioned before, is that we have a very, very small, heavy, and dense star. And so the magnetic field is very, very strong. Basically, the magnetic flux was retained from when the star was a normal star, a full-size star. And if the star shrinks by a factor of, say, 1,000,000, the intensity of the magnetic field has to grow by a lot to compensate for the surface area going down. So flux is, of course, surface area times strength of the field. If the radius goes down by 1,000,000, the surface area goes down by 10 to the 12. And so the magnetic field has to grow by approximately the same amount or same factor, about 10 to the 12. So a trillion times stronger than the average magnetic field of a star, say like our sun. If these magnetic field lines surrounding the magnetic axis are not directly perfectly aligned with the orbital or spin axis, the spin axis of the pulsar, of the neutron star, then as the star spins, say it spins this way, the magnetic field will spin with it and the direction of the magnetic field will change. And so every time the magnetic field points towards us, it will excite particles and radiation in our direction, and we'll see a pulse of radiation. and then will be the off state as it turns away. And we get this, these beams of radiation and matter pointing to us on a periodic fashion. We can use this model to calculate or estimate the dimensions of the star. And like I said, if we can kind of give a limit on it, which is saying that we want to relate the velocity of the outermost part of the star, the surface of the star, to the orbital period t, or frequency, orbital frequency omega. And of course, v equals omega r, or 2 pi over r. That means that the radius is the velocity times the velocity times the period divided by 2 pi. That's basically just 5th grade math. Distance is velocity times time. But now we can use the physical constraint that the velocity has to be less than the speed of light, because nothing can travel or spin faster than the speed of light. And that gives us a limit if we put in the time as order of a millisecond and the speed of light as 3 times 10 to the 8 meters, or 10 to the 5 kilometers per second, we get an order of just 50 kilometers. So, and that's at the limit. If it were spinning with the speed of light, its radius would have to be less than 50 kilometers. If we started with a mass of about a solar mass and we condense it to a radius of 10 or a few tens of kilometers, we come to a typical density of about 10 to the 14 grams per centimeter cubed, about 10 to the 14 times more dense than the sun, or the average on Earth. And this brings us straight into the realm of nuclear physics and nuclear densities. And this was kind of the first hint that these things had to be, these pulsars had to be the effect of neutron stars. Because we have nuclear material, we have to condense neutrons to these densities. That answer brings up more questions than it helps answer, because we actually don't know how nuclear matter behaves at such large masses and densities. The nuclei we know go from about the mass of 1 neutron or 1 proton, which is hydrogen, to about 200, 260, maybe slightly more than that for the most unstable heavy isotopes and heavy elements, uranium, plutonium, and beyond that. But we don't know how more than, say, 300 nucleons or neutrons interact with each other. So we know that the regime is highly non-trivial. The strong nuclear force has to take effect there. The pressure would be neutron degeneracy pressure. It's not just gas pressure. Neutrons don't really interact with each other so much. So the typical thermodynamics of gases is inapplicable. It's a degeneracy pressure. It's a quantum effect that even holds the star together against gravity. And because the mass is so large and the density is so small, recall that for a solar mass, the Schwarzschild radius is only about 3 kilometers. So we're talking here about something that's maybe 10, 20 kilometers. It's a significant fraction, maybe more than 10% of the Schwarzschild radius, or 10 times the Schwarzschild radius, which means the density, the relativistic parameter here would be something like 10%, means that you need to solve the equation of state as a relativistic equation, a general relativistic equation, and that gives us this Tolman-Oppenheimer-Volkov equation relating the density rho, pressure P, mass distribution R of the star. Even just to solve hydrostatic equilibrium, you need to solve this relativistic equation. And you can see here the Schwarzschild radius coming in. And we don't know how the pressure is actually related to the density in this regime, so we can't actually solve this equation, even when we can write it. So we have estimates of this bound on a neutron star limit mass of about 1.4 to 3 solar masses, but we don't actually know the correct answer. And we would like to. The only way to do that is to study a very large number of these neutron star systems, both in separate static scenarios and in dynamical situations, which we'll talk about more, to try to infer the equation of state, to ask how does the thermodynamics and statistical mechanics of this nuclear matter that's dense and massive behave. And of course, we have to take care both of gravitational effects, GR effects, of nuclear interactions, of strong and weak nuclear interactions, and gravity, which might even be quantum on this energy scales and densities. And even that only applies to some of the more outer parts of the neutron star, where we think it is actually a neutron star that is composed of isolated neutrons or distinguished neutrons. Maybe a lot of them, maybe they're packed together, but we can still think of them as neutrons standing next to each other. Further in, when you condense them together, we might even reach this question mark here on the diagram, where the neutrons start to mesh into each other. And then basically the quarks in one neutron can interact directly with the quarks in the other neutron. And we get kind of this quark gluon plasma of quark matter and gluons mediating the strong nuclear force all together in a state of matter with which we have no experience on the Earth, because we are not really capable of producing these high energies at these masses and densities to even explore that. So we're kind of, these neutron stars and possibly quark stars or strange stars or whatever is in the middle is challenging in a lot of physical fronts today of research, and is the active scene of a lot of research today. What we have is multiple suggestions for equations of state. Each one of them here has a name, SQM1, AP3, a lot of suggestions. Each of these equations of state gives a slightly different prediction for the relation between the mass and the radius of the neutron star. You can think of that as kind of giving a different polytropic equation or polytropic index for the equation determining the star in equilibrium. And what we do is gather more and more of these equations, try to plot them, and eventually try to confirm or rule them out with experiments and observations. So back like 10, 20 years ago, it was thought that the equation of state should have an upper limit around between 1.5 to 2 solar masses. Then we started observing, here on the left, a list of observed neutron stars. We started observing neutron stars with very high masses. For example, this one here is from an X-ray binary, and you can see that while the error is the uncertainty is very large, it's centered around 2.4 solar masses. Or this one on top here, with a very narrow uncertainty error margin, also centered around 2.3 or 2.4. Once we have these, you can already kind of throw out the low mass limit neutron star equation of state proposals, because they don't explain all of the observations, or because they predict an upper limit and we've surpassed that limit. So all we have here is basically observations of neutron stars occupying various masses on the range. All of them are around the Chandra cycle mass, but some of them can be a little below or a little above, and trying to match them to equations of state, either on theoretical grounds or on theoretical constraints, like assuming limits on causality of sound waves, or of normalizing the pressure, or eventually of collapse to a black hole, which is the Schwarzschild radius. Another way to think of these masses is the plot here on the bottom. showing the range of electromagnetically detected neutron stars over the last few years or a couple of decades. Again, most of them occupy the range between 1 and 2, but we see these small excursions even above 2 solar masses. And now we're starting to also see some of the neutron stars in close pairs close enough to emit gravitational waves, like this orange pair here in the middle, which merged together. We saw the gravitational waves leading up to the merger, producing a body here in gray with a question mark. We don't know what that object was. We have not seen the result of this merger. We saw black holes here in purple starting to occupy the range from 5 solar masses and above. But in the gap here between 2 and 5, we don't actually know where the transition is from neutron stars to black holes, or maybe to other types of strange stars in between. Any questions?
I have a question. It's a
Yes.
few slides up though.
Well,
it's in the pulsars slide.
yes.
One more, yes, this one. Okay, so what we see from the pulsars is the electromagnetic radiation, basically. That's the pulsars.
Yes.
And if the spin ax is aligned with the magnetic field, we should see the pulsar not pulsating, right? We should see it.
Or not see it at all.
Or not see it at all if it's upside down. So
it's not so much upside down as much as the tilt. If my hand is the spin axis, and this is the magnetic axis, and then if it were this way, you would never see it because the radiation goes up and down and you're in front. Okay? Right. If it were like this, say 90 degrees, then as it spins, it would now pass through to you. So here you see the pulse and now it's gone. Until it rotates again, and I see a pulse, and then it's gone. Or in a more typical scenario, when the axis is not exactly perpendicular to you, it can be something like say that direction, say over here, and now you can see that the rotation will be something like this. Now it points to you, now it's gone, now it points back to you, and so on and so forth. So you'll have this rotation, and whenever the magnetic field turns to us, we can see it.
Okay, so a pulsar is basically just a spinning neutron star.
Yeah.
It spins fast enough, then it creates electromagnetic radiation.
The magnetic field is there, so it excites particles all the time. But when it points to us, then we see this pulse of radiation. It's really not a pulsar. It should probably better be described as a rotator, right? Or a spin star. They're not pulsars. They're not pulsars. The star is emitting radiation continuously.
Constantly.
But we see it as pulses because we only look at from one direction.
Yes, it's only pulses for us viewing it.
Exactly. We see it as a pulsar. We see the rotating energy only when it points to us.
But why does only neutron stars create such a strong magnetic field? Is it because it's dense, it rotates much faster?
So a white dwarf will also have a strong magnetic field, and it can also spin very fast. But if you just do the order of magnitude calculations, take the sun, for example. So the sun has a radius of 700,000 kilometers and a period of rotation of about 30 days. And the magnetic field, which is on average, say maybe 1 Gauss. Plus minus a few orders of magnitude doesn't matter. Let's call it 1 Gauss. If you shrink the sun by a factor of 100 to something of the radius of 6,000 kilometers, like the Earth, then you're doing two things. One, to conserve magnetic flux, you reduce the area by 100 squared, so by 10,000. So the magnetic field would have to grow to about 10,000 Gauss. So the magnetic field is stronger by r squared. It's much stronger. You're also increasing the rotation because you have to conserve angular momentum. And angular momentum goes like I omega, the moment of inertia goes like r squared. So again, if r shrinks by a factor of 100, I shrinks by a factor of 10,000, which means omega would have to grow by a factor of 10,000. So now a white dwarf replacing the sun, instead of rotating every 30 days, which is about 1,000 hours, would rotate every 1,000 hours divided by 10,000, so every 10th of an hour, okay, or every 6 minutes. So it's rotating a lot faster, and the magnetic field is much stronger. The next stage is taking that neutron star and shrinking it by another factor of 100 or 200 or 1,000 to something with a radius of about 10 kilometers, or say even 60 kilometers. So another factor, a clean factor of 100. That means another 10,000 in period reduction and another 10,000 increase in magnetic field. So from 10,000 Gauss, we would now go to 100 million Gauss. And from a 6-minute period, we would go to 6 minutes divided by 10,000. So 360 seconds divided by 10,000. So 36 milliseconds, basically. And those are the numbers that we see, for example, for these pulsars, for the Crab pulsar, right? 33 millisecond period.
See. Okay, thank you.
Alon asks, why would neutron stars emit magnetic fields? Aren't neutrons electrically neutral? What causes the magnetic fields? Okay, so first of all, many objects which are neutral electrically have a magnetic field. And the most famous of those is the magnet, the bar magnet, right? A piece of iron or a piece of rock with iron in it. And it can have a magnetic field. It would be a dipole magnetic field, basically coming from it being ferromagnetic. Ferro means like ferrum, like iron, that is a magnetic field resembling that of iron, coming from the spins in the iron atoms, all basically pointing in the same direction, and they can maintain themselves like that for a very long time, a permanent magnet. Up to temperature and other solid state effects, but generally the atomic spins in iron can maintain the magnetic field. And neutrons, while having no electric charge, do have a magnetic spin. There's particles with spin. They're fermions. They have a fractional spin, a half spin. And they can, if those spins are oriented in the same direction, they can have a magnetic field and it can be sustained. When the star collapses, whatever magnetic field was there before will change, but the flux will be mostly conserved adiabatically. And so the neutron star will anchor whatever magnetic field is left. But it doesn't have to be charged to do that. Okay? Does that answer the question? Alon? So the spin in the neutron stars. So again, you have to check exactly what is causing this magnetic field, but one way to do it would be with the spin angular momentum. You can also think of the crust of the neutron star represented here. Some of the crust might contain still a few electrons or protons. You can think of the superfluid in between actually having a fluid rotating and maintaining these currents and fields. There are many ways to do it. You'd have to go deeper into the constitution and composition of the neutron star to see exactly what is holding this magnetic field. But there's definitely enough matter to do it in multiple ways. Okay. So much for supernovae and neutron stars. If we go back to the beginning, as energetic and important as supernova phenomena are, supernovae, they're still only about 1 billion times the solar luminosity and still 10 to the 14 orders of magnitude or 14 orders of magnitude away from the absolute limit of the Planck Dyson luminosity. And we see here that about 1 million times stronger are these GRBs, gamma ray bursts. So let's look at those. At gamma ray bursts, and the history here is much shorter than the history of supernovae. We mentioned supernovae were documented even the years BCE, before the Common Era, meticulously documented in the optical from Kepler's time and then Tycho's time, and even earlier than that in outside of Europe. Gamma ray bursts were discovered only very recently. And the reason for that is that they emit in gamma rays. And we were not able to detect gamma rays until quite recently. Luckily, our atmosphere blocks gamma rays. Otherwise, we would be fried. And so we needed satellites to do this. And in fact, the 1960s did see many satellites launched looking for gamma ray emissions, not in space, but on the Earth itself. Nobody expected these to appear. But it was the Cold War, and the Russians and Americans were detonating nuclear bombs and experimenting with them a lot. And at some point, they signed a treaty to ban nuclear tests and experiments. And to make sure that the Soviets were obeying the treaty, the Americans launched satellites to measure gamma rays, a trace of nuclear activity explosions on Earth. They wanted to see that if there's a nuclear bomb going off, they can bring the evidence and tell the Russians, you're not playing by the rules. And what those American satellites discovered was a gamma ray burst basically every day, which was a great shock to the Americans and almost started a world war. But they quickly realized that these gamma ray bursts were not coming from the Earth. They were coming from space to the Earth at a very fast pace, about 1 a day, releasing huge amounts of radiation, 10 to the 18 solar luminosities, so even much stronger than a supernova. And they noticed that not only were they not coming from the Earth, they were coming from all around the Earth. All around the Earth and very energetic. And if you recall last week's discussion about the shape of the galaxy and spherical symmetry, this indicates that they come from outside the galaxy. Because if they were coming only from our galaxy, we would expect a preference to the galactic plane. We'd see more denser or a more probable emission of gamma ray bursts from the galactic plane. And we don't see that. We see them coming from all around the sky, which means they're not in our galaxy, they come from other galaxies all around. This meant a few conclusions. One was that they were much more energetic than previously thought, because of course, what we measure is only the observed luminosity. The further something is, the higher its absolute luminosity. And so that number grew by a lot. But with that came the realization that in order to release so much energy in so little time and so far away, the gamma ray burst has to beam the energy. We can't be seeing them. It can't be a spherically symmetric source. It has to be a very, very narrow source, a jet basically, a beam or a jet. And that's very possible to do, right? We saw that. Lorentz contraction would do that. Very, very fast ultra-relativistic source would cause Lorentz contraction in one direction relative to the plane parallel, no, perpendicular to it. And so you'd get this beam of energy narrowing the spherical emission to a jet, to going into a beam in one direction. And so these gamma ray bursts were understood to be beams of ultra-relativistic energy, a lot of energy, basically such large energy and power and such high relativistic velocities must involve a compact object as a source, because only then you can have enough gravity to give enough kinetic energy to whatever you're accelerating. And so people started looking for various mechanisms involving compact objects as the engines of those GRBs. New satellites showed that there were actually two types of GRBs. You can see here separated in the duration of the GRB. And you can see number of bursts in each of these time bins in the histogram. And people typically use that 2-second mark to distinguish between what is called short GRBs and long GRBs. The long GRBs lasting for more than 2 seconds, the short duration GRBs lasting for less than 2 seconds. This is from the BATSI GRB instrument. Here below you see also the kind of the spectrum, the hardness of the spectrum, or the ratio of high energy photons between 50 to 100 keV to the lower energy photons 25 to 50 keV. So this kind of tells you whether the spectrum is slanted towards the high energy or towards the low energy. It gives you an indication of the composition of this energy. And again, you see the separation basically follows the separation in duration, with long GRBs being slightly lower in this ratio and short GRBs being a bit higher. We still don't know what the actual mechanism is behind long and short GRBs. We think short GRBs accompany mergers of neutron stars, a binary neutron star merger. And we'll talk about those in a moment, but there's still many more questions than answers in this field of understanding and modeling GRBs. These ultra energetic explosions in the sky, beams in the sky, a million times brighter than even supernovae. Any questions?
Yes, I was wondering, because gamma rays are a really strong ionizing radiation, if we feel that, if we feel them as humans on Earth, or if the atmosphere disrupts them.
The atmosphere protects us from gamma rays, basically. Now, there are these considerations. People say that if the Earth were closer to the center of the galaxy, maybe, or to a GRB active region, there would be strong enough GRBs, even in our own galaxy, to pass the atmosphere and kill us all and stop evolution. And one of the proposed solutions to the Fermi paradox of why we don't see other civilizations is because most of the galaxy is actually hostile to life, because GRBs would kill them before they get to evolve. Whether that's true or not, we are far enough. We have few GRBs in our vicinity. It's been a while since we saw one in our own galaxy, and we have an atmosphere, so we're basically safe from this gamma radiation so far, and we can live.
Okay, thank you.
Okay, there's kind of an outline of a model of a GRB on this slide, showing some compact object as an engine, blasting off matter very, very fast. That matter then produces this type of jet. The jet itself is ultra-relativistic, but as it comes into outside matter, it can slow down, and we have shocks and reverse shocks. And these processes will all produce different types of high-energy photons. We see here all across the spectrum of radio visible X-rays, gamma rays, and very high-energy gamma rays. But again, modeling the jets and modeling the source are separate things, and we don't know a lot of things about, there are many questions still asked about both of them. Which leads us to the next object up our hierarchy of energy, and that's mergers of compact objects driven by gravitational waves. So we remember that two compact objects like black holes, neutron stars, or a black hole neutron star pair will orbit around each other from gravity. Changing the quadrupole moment will emit gravitational waves, carrying energy from the orbital energy of the system, causing the bodies to fall on each other or to spiral into each other. That's an in-spiral. Kepler's law then tells us that the frequency would increase, then the quadrupole emission would increase, and we'd see one of those typical chirps here on the bottom right, with both the frequency and amplitude and power, the brightness, going up in time. How late or how long can this process continue? Until they merge or really fall on each other, or if you're a little more conservative, until they reach the ISCO, the innermost stable circular orbit, and then they don't in-spiral anymore, they plunge onto each other. How much power do they put out? Well, we can estimate that as well from the same quadrupole formula. So we call the quadrupole formula is similar to the electromagnetic Larmor formula or dipole formula, but one order up. So it has G because it's gravitational and C to the fifth, the reduced mass mu squared, and it depends on the quadrupole moment. So the mass squared, the radius is to the fourth power, because the quadrupole moment is UR squared, then square that up to numerical factors, and the sixth power of the frequency, omega to the sixth. This is in units of power, that is energy per unit time. And we can try to understand it or kind of massage this expression if we separate it to units of force. G times mass squared divided by distance squared is Newton's law for the gravitational force. So this has units of force times distance. Force times distance will give us units of energy. Time, omega, will give us units of 1 over time. So now this part is force times distance divided by time, exactly units of power. And what's left here in parentheses is dimensionless. Omega to the fifth or to the fifth, that gives us distance divided by time. So velocity normalized by the speed of light, that's a dimensionless number. Okay, massaging this a bit further, we can replace the reduced mass by the symmetric mass ratio if we use the total mass m, and now we have kind of another dimensionless factor, this eta, which has no units, up in front, with some measure of the Newtonian force, gm squared over r squared for the total mass. And we can compact all these omegas and r's into v to the sixth or v to the c over 6. So now we have, again, a dimensionless number, eta squared, a measure of force, the speed of light, and another dimensionless number. We can identify the Planck Dyson luminosity, which we saw in the beginning. That's this c to the fifth over g. Okay, so we kind of, power, as we said, is dimensionless in GR units. So we'll isolate all the units from the non-dimensional parts. We do that to the first term. Gm squared over r squared has units of force. But we recall that Gm over c squared is the Schwarzschild radius. It has units of length. So we'll take this, we'll split this r squared and m squared. This is m squared over r squared. We'll split that into two pairs of m over r, putting in the g's and c's to fix the units as much as we need. And so we get Gm over c squared r squared is a dimensionless number, basically measuring how compact the system is. It's the ratio of the mass to the separation. Or if you want, the Schwarzschild radius divided by the separation radius. It measures how tightly knit the system is. And we'll call this parameter x, or its inverse x, r over m in GR units. V over c, we recognize as another dimensionless parameter. It's the relativistic parameter beta, the relativistic velocity beta, v over c. So this has no units. X has no units. All the units left in this expression are c to the 5th over g, the Planck Dyson luminosity. What this means is that the peak luminosity, the luminosity of a gravitational wave merger, is directly calculated from the Planck luminosity. We just have to understand what these dimensionless numbers are, get some typical numbers to understand what the scales are. And those typical values we can take for a black hole. If it's a Schwarzschild black hole, so it doesn't spin, the ISCO radius will be at 6, r equals 6m. Typical velocities for the plunge are about half the speed of light. And if it's equal mass or similar mass, the symmetric mass ratio is about 1/4. Plugging in those numbers, we come out with something like 1,000th, one over about 5,000 as a numerical factor, or 0.02% of the Planck Dyson luminosity. So at the end of the in spiral, when the two black holes are at the ISCO and starting to plunge, we're already at about 1 over 5,000 of the maximal possible luminosity for any physical process in nature. Okay, this is the highest luminosity ever measured by humans from any process, the end stage of the merger of two black holes. Any questions? Okay. So finally, we'll talk about gravitational waves from binary neutron star mergers or BNS mergers. The behavior here is very similar to a binary black hole merger, and we can see here below the LIGO-Hanford and LIGO-Livingston chirp tracks for frequency and amplitude as a function of time for the single certain BNS merger event we've measured to date, GW 1708. I have to correct this number, 170817 on 17th of August, 2017. It was identified to be in a galaxy about 40 megaparsecs away. And it was identified because we saw a counterpart in other telescopes. In fact, we saw a counterpart in all the other telescopes, because after this event was registered in a gravitational wave, every telescope or satellite on and off the Earth were pointed at this, looking for this event, looking for this galaxy, trying to see the source. And here we see on the left, the host galaxy, and we see this kind of star appearing on August 22nd, so 5 days later, and then another 4 days and another 2 days, dimming after its original appearance. On the right, we can see the original non-gravitational wave detection, the Fermi gamma ray burst detection accompanying this event, starting almost immediately after the peak of the chirp. So we saw gamma rays, and then later also the source appeared in X-ray measurements, UV measurements, optical measurements, infrared radio, all across the spectrum. We saw this, the gravitational wave signal driving the system to a merger. And then when the two binary neutron stars hit each other, there's an explosion which registers as a short GRB. And after that, the object can be seen to appear basically in every telescope or instrument that we have. In all of them, you see the light from the galaxy in the middle, and this little point appearing as a transient 11 hours later, 9 days later, etc. the appearance of this multi-messenger event. We saw it both in gravitational waves and in electromagnetic instruments. Any questions?
Yes. Have we detected any binary black hole merger visually, or only by the gravitational waves detectors?
Only by gravitational waves. The problem with black hole mergers, binary black hole mergers, is that there's no matter. There's no matter to create electromagnetic radiation. There are no neutrons, no electrons, no protons. It's just black. It's just a hole in space-time. So we don't expect electromagnetic counterparts. We're looking for them, but we haven't seen any of them yet, and we're not surprised that we haven't seen them yet.
Mm-hmm.
For a binary neutron star, you do expect a counterpart, at least if it's kind of aimed in the correct direction to point towards you. And this one luckily was.
I see.
There were possibly other BNS mergers. One of them is listed here, GW 190425. That is, the masses match the range we expect for a BNS merger, but we haven't seen a counterpart, so we cannot be sure. The final thing to say is that these BNS mergers are really just colliding together huge multiple solar mass, 1 or 2 solar masses each of almost pure neutrons. So these have no problem in producing our process elements and all of the heavy elements that we know and love: plutonium, uranium, here's gold and silver. All of these elements are produced almost exclusively in the universe in binary neutron star mergers. And after they collide and the explosion spreads away these elements all across the universe. So like this ring that I have on my finger, this gold ring was produced from the remnants of supernovae and BNS mergers, reaching the Earth a long, long time ago. That's it for today. Any more questions?
Yes, I'm still a bit perplexed because we spoke of luminosity, and the strongest luminosity should be at the moment of a black binary black hole system.
Mm-hmm.
And I consider luminosity as light, and if there's no light, how do we know, besides the theoretical calculations, if there's zero light, how do we know that it does has the peak luminosity?
So luminosity is power. It's energy coming out of a system. Mm-hmm. And traditionally, in traditional astronomy, luminosity was measured across the electromagnetic spectrum. First in the optical and the visual range, later IR, infrared, UV, radio, X-ray, gamma rays. But now, since 1987, maybe even earlier if you consider the sun itself, we have other types of energy coming out of sources. We have neutrinos coming out from the sun, coming out from supernova 1987A. We measure neutrinos coming around from the sky. And as of 2015, we also measure gravitational waves coming out and reaching us from far away in the sky. And this is just another messenger, it's called. But today, in the age of multi-messenger astronomy, it's a perfectly legitimate way to send energy from one place to the other in the form of neutrinos, of matter, or in gravitational waves. And in fact, the most luminous, the most efficient ways of producing power in the universe do not involve electromagnetism, which kind of ties you down to matter. And gravity is much more efficient in producing energy. So gravitational waves are in fact more efficient, and the most luminous objects in the universe are gravitational wave sources from black holes and not electromagnetic sources.
Okay, I get it now. Thank you.
Any more questions? Okay, if not, I'm stopping the recording.